Let's take a look at one more example of a related rates problem. This is one of my personal favorites. A boy on a bicycle passes underneath a balloon when the balloon is 45 feet high. This example, really what it does is it brings back why we were talking about helium-filled balloons in the first place. The balloon is rising at a nice constant 5 feet per second, and the boy is cycling at 15 feet per second. How fast is the distance between the boy and the balloon increasing 3 seconds later? So let's make ourselves a little picture of the situation. Make a little balloon up in the sky and boy on a bicycle. Oh boy, okay. Bicycle. Nope. You're now on a scooter. So that'll work. The boy is traveling in this direction at 15 feet per second, and the balloon is traveling in the upward direction at 5 feet per second. So what's going to happen is 3 seconds after this takes place, the boy will have traveled a little bit more this way, and the balloon will have traveled a little more this way. Now, we are being posed a question about the distance in between the boy and the balloon. Now, you'll notice, though, that all that this is doing is really just creating a big old right triangle for us. So I'm going to have us start with D, define, and I'm going to say let x be the horizontal distance traveled by the boy. So that'll represent this side of the right triangle right down here. We'll let y be the vertical distance for the balloon. So that'll be this side over here. Starts out at 45, but then starts increasing after that. And we will let z be the actual distance between them. What I might refer to as the slanty distance. Now, as far as relating these three variables, these three are now the sides of a right triangle. Best way to represent a relationship for the three sides of a right triangle, well, that would be leg squared plus leg squared is equal to hypotenuse squared. So that'll be x squared plus y squared is equal to z squared. Then let's go ahead and implicitly differentiate with respect to t. So we're going to differentiate with respect to t, x squared plus y squared. And we're also going to differentiate with respect to t, z squared. So first thing I'm going to do is actually perform this differentiation, and then we'll talk about what all of the variables mean in this relationship. So differentiating x squared with respect to x would be 2x. So with respect to t, it'll be 2x times dx over dt. Same thing for y squared. Derivative of y squared with respect to y would be 2y. So with respect to t, it'll be 2y times dy dt. And the same thing over on the right-hand side. That'll be 2z times dz over dt. Now, if we reread the problem, there are some quantities that we know, and there are some quantities that we are going to figure out by doing some extra work. So the first one is calculating the actual value of x at this instant. Boy is traveling at 15 feet per second, and it is now 3 seconds later. So instantaneous quantities, we'll call these IQ over here. X would be equal to 3 seconds for the time times 15 feet per second to give us 45 feet. Now, as far as y is concerned, y already started 45 feet in the air, and then it continued to rise for 3 seconds at 5 feet per second. So initial position plus time times the speed, that gives us 60. And as far as figuring out z is concerned, we have that z is equal to the square root of x squared plus y squared. If you plug in that 45 and that 60, you will get that this is 75. In fact, what you have here with these three sides is simply 15 times my favorite right triangle, the old 3, 4, 5 right triangle. So 3 times 15, 4 times 15, and 5 times 15. Additionally, we also know that dx over dt represents the speed at which the boy is traveling, and dy dt would represent the speed at which the balloon is rising. So the other quantities that we know that dx over dt is going to be equal to 15, and that dy over dt is equal to 5. What we're going to do is plug in all 5 of these quantities and solve for the one quantity that we don't know. Now, before I go ahead and plug that in, I am going to do one small thing that's going to make this process a little bit easier and get rid of all of these extraneous 2's that we have in here. So this will just be x times dx dt. So that's 45 times 15. Those are the quantities that we had from over here. Plus, no more 2, just a y, which is 60, times dy dt, which we said was equal to 5. And that's going to be equal to, no more 2. We'll have z, which is 75, times dz dt, which is the thing that we're trying to find. So this step would be the P of our DRIPS process, where we plug stuff in. Then we actually solve for the quantity that we're trying to get. That'll be dz over dt is equal to 45 times 15 plus 60 times 5 all over 75. I actually don't have a calculator in the room with me. This is a little bit embarrassing. So what I am going to do is say, for the first term, we can reduce the 15 over 75 to be 1 over 5, and then 45 divided by 5 would be 9. And for the second term, we can reduce the 5 and the 75 to 1 over 15. 60 over 15 will be 4. So final answer for this one numerically is going to be 13. To interpret this answer, we would need to include units on it, and every single thing that we did for speeds in here were feet per second, feet per second. Therefore, our units will also be feet per second. That one felt good. I'm going to give it my favorite onomatopoeia. Kapow!